Hi everyone, I am Arturo Pascuzzo and I'm from the University of Calabria in Italy. The work that I'm going to present is about a novel crack-growth propagation modeling based on the combination of moving mesh method and the interaction integral approach. This work is co-authored with D.Ammendolea, Fabrizio Greco, Paolo Leonetti and Paolo Blasi from University of Calabria. Crack-growth phenomena appear in several applications of mechanics engineering fields, and numerical simulations are frequently used to assess the vulnerability and reliability of damaged materials and components. Several numerical approaches have been developed to analyze crack propagation phenomena. They can be classified in geometric and non-geometric approaches. The geometric approaches represent the crack by a geometric entity, while the non-geometric approaches account for the presence of discontinuities, adopting constitutive degradation models or refined cinematic models. Each modeling approach presents negative and positive features, thus noting that a unique and optimum approach does not exist. Currently, new efficient numerical methods able to predict crack evolution within damaged materials with less computational errors are much required. This work we present an efficient finite element numerical modeling which combines moving mesh methodology and fracture mechanics concept to predict crack growth propagation in linear elastic continuum media. The moving mesh method, based on the arbitrary Lagrangian-Eulerian formulation, is adopted to appropriately describe the evolution of discontinuities within computational domain. The interaction integral method is employed to accurately evaluate the stress intensity factors of the crack problem. This presentation is structured in 4 parts. In part 1, the theoretical formulations of the arbitrary Lagrangian-Eulerian method and that of the interaction integral method are described. In part 2, the numerical implementation is reported. Part 3 presents the numerical application of the proposed modeling approach. Finally, in part 4, some final remarks are discussed. The arbitrary Lagrangian-Eulerian formulation is based on the definition of 2 coordinate systems, which are known as referential and moving coordinate systems. The referential system identifies the computational nodes in their initial position, whereas the moving system provides the position of the nodal points during the movement process. A proper mapping function links the systems and allows defining the gradient operator of the transformation, which is needed to express governing equations in the movement configuration. The governing equations of the problem comprise 2 contributions. The first concerns the equation of the moving mesh problem, which consists of the Laplacian regularization equation for reducing mesh element distortion and a constraint condition on nodal mesh displacement, which limits nodal displacement within the computational domain. The second set of equations consists on the definition of a crack growth criterion, which identify the condition of crack initiation and the direction of crack propagation at the tip front. The crack tip displacement is reproduced by imposing that the displacement of the computational node at the tip is equal to the incremental displacement provided by the crack growth criterion. The crack tip problem, which consists in the evaluation of the stress intensity factors, is solved by means of the interaction integral method. The interaction integral expression, also known as M-integral, can be obtained starting from the classical definition of the J-integral applied to a closed contour surrounding the crack tip. In the contour integral expression, Q is an arbitrary weight function with values varying smoothly from 1 to 0 by passing from the inner to the outer edge of the contour. For computational reasons, the J-integral is usually converted in a dominant integral form by applying the divergence theorem. Considering the superimposed J-integral for the actual and the actually filed, whose solution is completely known, the M-integral represents the last term of the superimposed state. The M-integral can be equivalently expressed in terms of the stress intensity factors, using the equivalence between the J-integral and the energy release rate. The governing equations are implemented within a finite element framework based on a Galerkin approximation. In this framework, the governing equations are expressed in a variational form. One relevant aspect consists in the definition of the fracture function and the direction of crack propagation. To this end, the maximum circumferential stress criterion has been used in the model. The stress intensity factors are evaluated by means of the MA integral, considering as a luxury state the solution of pure mode 1 and pure mode 2 of a strike crack in an infinitely large sheet. Here, more details regarding the propagation process are discussed. The intensity of the nodal mesh displacement vector of the crack tip is imposed equal to the incremental scalar quantity related to the crack advance. The angle of propagation is defined as the sum of pre-existing crack slope, evaluated with respect to a global coordinate system, and the instantaneous kinking angle, which is computed in the local crack system. A further condition is imposed in order to require that the shape of pre-existing cracks must not change. This condition is guaranteed by defining a small stretching segments near the crack tip describing the instantaneous propagation. A tolerance value of the angle variation of the stretching segment with respect to the local crack system is imposed. When this angle tolerance is satisfied, the geometry of the problem and then the computational node are updated. This strategy ensures a reduced number of remeshing procedures, thus promoting a great reduction of computational time. The proposed model is managed by an automatic algorithm which is summarized in this flowchart, noting that the remeshing processes are required exclusively when mesh regularity is compromised. In addition, the geometry of the problem is updated when the variation angle of the stretching segment reaches the tolerance value. In this part of the presentation, the results relative to the application of the proposed model to the analysis of crack propagation in damaged structure are presented. The first case consists of a double cantilever beam with a horizontal pre-crack at middle height, subjected to two distributed and opposite loads at the left extremity. Note that the right extremity of the pre-crack is slightly bent downwards. This condition will force the crack to grow toward the bottom portion of the beam. The obtained results confirm such a crack path. In particular, during the earliest stage of propagation, the crack path is characterized by a highly pronounced curvature. The obtained results have been compared with the experimental data and predictions of other advanced numerical methodologies. The accuracy of the proposed method to properly reproduce the crack path prediction is confirmed. The second application consists of a pre-crack rectangular plate containing an off-center circular hole under normal traction along the top and bottom edges. Here, the main aim consists to investigate the effect of the hole's presence on the crack path. This case has been first analyzed in the seminal work of Rashid in 1998. Rashid investigated the crack growth by means of the arbitrary local mesh replacement method. Comparison results denote that the proposed method properly reproduced the result obtained by Rashid, thus highlighting high accuracy to predict the effect of the hole's presence. The same geometry has been analyzed considering the effect of an inclusion's presence. In particular, the analysis focused on the evolution of the crack path due to the presence of a soft and hard inclusion. In the case of a soft inclusion, the crack path is quite similar to that of the plate with the hole. This behavior becomes more evident for softer inclusions. On the other hand, considering an hard inclusion, the crack path is quite straight. This case denotes that the stiffness of the inclusion highly affects the crack path development. In conclusion, we present a new finite element numerical modeling approach able to predict crack growth phenomena in linear elastic continuum media. The proposed approach combines the moving mesh methodology based on an arbitrary Lagrangian-Eulerian formulation to depict crack growth and evolution and interaction interval method for evaluating the stress intensity factors of the crack problem. The crack growth is simulated by means of a geometric variation of the internal discontinuities of the computational domain. Despite existing formulations, the proposed model reduces the recurse to remeshing events, which typically require substantial computational costs. Comparisons between the proposed method and experimental results and predictions of different numerical strategies have denoted that the use of the proposed method ensures accurate predictions.